Peptides are short polymers formed from the linking in a defined order of alpha amino acids. The link between one amino acid residue and the next is known as an amide bond or a peptide bond. Proteins are large organic compounds made of amino acids arranged in a linear chain and joined together by peptide bonds between the carboxyl and amino groups of adjacent amino acid residues. There are different structures of protein. First of all, the primary structure of protein is the simple linear sequence of its amino acid structural units. The secondary structure of protein occurs when the sequence of amino acids are linked by hydrogen bonds. Tertiary structure is the three-dimensional structure of the polypeptide. It occurs when certain attractions are present between alpha helices and depleted sheets. Finally, quaternary structure. The structure is formed by two or more polypeptide chains associated by non-covalent force. So what are the functions of proteins? Transport and storage of small molecules, coordinated motion via muscle contraction, mechanical support from fibrous proteins, and enzymatic catalysis. Uses of proteins are very important for our bodies. For example, tissue plasminogen activator is used for heart attack and stroke. Oxytocin maintains the labor pain. Bradykinins increase the peripheral circulation, and insulin maintains blood sugar level. Most pharmaceutical proteins and peptides are formulated as solution or suspensions and delivered by invasive routes such as intramuscular, intravenous, or subcutaneous injections. These routes have their own disadvantages like poor patient compliance and inconvenience to pediatric patients. The oral route presents a series of advantages towards other drug delivery systems like its most convenient route of drug administration, avoidance of pain and discomfort associated with injections, higher patient compliance. Due to the importance of oral routes of administration, scientists tried to develop new approaches in order to reach higher efficiency and satisfaction levels for the patient. And for that, researchers faced several challenges because of the physicochemical properties of proteins. These physicochemical properties include large molecular size, susceptibility to enzymatic degradation, short plasma half-life, high immunogenicity, tendency to undergo denaturation, and less bioavailability. Pharmaceutical approaches for proper oral delivery of proteins include, firstly, chemical modifications, which include amino acid modification and hydrophobization, enzyme inhibitors such as protease inhibitors, penetration enhancers, and formulation vehicles. One of the most challenging problems in the development of liquid, peptide, or protein pharmaceuticals is the physical and chemical instability. Stabilization of peptides and the proteins in designated delivery system against the degradation can be carried out by using several excipients such as salts, amino acids, and carbohydrates. Ketosan are non-toxic, degradable, and biocompatible polymers. The presence of free NH2 groups allow ketosan to form polyelectrolyte complexes with negatively charged moieties. Such polyelectrolyte complexes are to increase protein stability towards harsh conditions in the GIT and to protect them against physical and chemical instabilities. A physically stable system depends upon the molecular weight of low molecular weight ketosan. For example, low molecular weight ketosans of shorter chains formed soluble complexes, while turbidity and precipitations were observed with higher molecular weight, low molecular weight ketosans. On the other hand, the chemical stability of insulin was affected to the same extent in the presence of different molecular weight, low molecular weight ketosans. This may be attributed to the ratio of ionized groups of insulin to ketosan. Insulin instability was observed mainly at high concentrations. This may be explained by the changes in low molecular weight ketosan structure and particle size with concentration. The structure becomes more helical, leading to the formation of aggregates and an increase in particle size. Such aggregates may prevent low molecular weight ketosans from protecting insulin. The results for the in vitro release of insulin showed a negligible release at pH 1.2, while at pH 6.8 the release is markedly increased. ELISA method is used for determination of insulin bioactivity. The ELISA method has very high sensitivity and specificity as it depends on the reaction of the predominant protein with a specific antibody to form a complex. Therefore, ELISA antigenicity is considered to be an appropriate means for detection of changes of insulin antigenic activity. The protective ability of the reverse micelle under conditions simulating the gastric environment was evaluated. Free insulin was found to be completely degraded during incubation with pepsin, while in the reverse micelle about 90% of insulin was recovered. These results emphasize the importance of the reverse micelle system in the protection of insulin from degradation by pepsin. Decrease in plasma glucose level was observed after oral administration of insulin complex after solubilization in the reverse micelle. The decrease in blood glucose levels may be attributed to the improved stability of insulin in the reverse micelle preparation against degradation at gastric pH values and in the presence of enzymes in the GIT system.